Welcome to lab number 2 for ECE 441A 541A, and this video or lab is concerned with feedback, and in particular constant gain feedback. And what we want to obtain from lab number 2 is a little insight into why and how we can change how this system behaves or its response characteristics by using feedback. Here is our mass spring damper system that we've been dealing with this semester. It's a second order system. It involves positions, velocities relative to mass number, or this particular mass, whatever your mass is. It has a spring constant K. It has a damping constant B, and we're applying a force that actually has a hardware aspect to it, or a hardware gain. We apply this input that we've been using in units of counts, and that goes through the mechanical and electrical interconnections to produce the force applied to that mass M. We should be comfortable with describing the behavior, the dynamic behavior of that system by now. It's M x double dot or x double prime. So mass times the acceleration of that mass plus B, the damping coefficient, times its velocity, plus the spring constant K times the position, and that equals this applied force, which is determined by this hardware constant K sub hardware times U. We can solve that for the acceleration to provide us a way to think about this mechanical system in the form of a block diagram. And you can see then that if we had the signal x double prime, let me change colors. Here is our acceleration signal, and if we send that through an integrator, that will produce the velocity. We integrate the velocity, that will give us a position. Now we have access to, in this block diagram, position, velocity, and acceleration, and we know that acceleration needs to be created from these signals in our system by 1 over m. That's this scaling constant that I've introduced to the left of the acceleration, and that will now scale minus bx prime. That's then the first signal that we see moving in a clockwise direction from the input to that scaling factor 1 over m in the summing junction. We have minus kx and plus k hardware u. And remember, in our lab number 1, this input u that we applied was in fact a scaled version of our desired response, which was to move 2,000 counts with our position of that mass and hold that for 3 seconds, then turn that signal off and come back to rest for between 3 and 6. Then we hit it again with the same amplitude of 2,000 and rest for 3 seconds, and again hit it again, just to see if we could duplicate that behavior. We could now use Mason's gain to find the transfer function between the input R and the output X, or we could go back to the time domain differential equation, Laplace transform that. We should be able to, with that analysis, find the transfer function between the input u. Right now we're not concerned with k sub pf and r, we're just going from u to x. Then that will give us this open loop transfer function of our system as a second order dynamic behavior determined by the denominator polynomial, and you can see that that's influenced the dynamics of your system are influenced by that damping coefficient B and the spring constant K, and we have a numerator factor that is K hardware divided by the mass. And obviously that open loop transfer function will depend on your particular spring constant and your mass. K hardware is going to differ a little bit between the systems, and the damping coefficient will also vary slightly between the different systems that you're playing with. But based on this second order system, we can now view those roots of the denominator, or the poles of our system that I've indicated now with an X, as sitting somewhere, and I've now just shown you the positive half of the complex S-plane. It has a conjugate pole mirror imaged below the real axis, and it would then be sitting at minus sigma minus j omega sub d. But you can now see that we can describe these second order systems governed by this mass spring damper system in terms of a real part and an imaginary part, where omega sub d is our damped frequency of oscillation, sigma is our real part or component of the poles, and that gives us our damping. And by Pythagorean theorem, we can now see that we have this hypotenuse, which is in fact the distance that pole is away from the origin, is our natural frequency. We now have the relationships. We could write it in rectangular form as minus sigma, that's the real part, plus j omega sub d. Or if we wanted to, we could think also in terms of this angle theta, and that theta angle is related to zeta, where zeta now, if we remember that sigma can be thought of, or if you just compare this standard notation on the far right with the rectangular description of your poles, we can see that sigma is zeta omega sub n. We know what omega sub n is. If we find the cosine of that angle theta, that's now just the adjacent side, which is sigma, or zeta omega sub n, over the hypotenuse, or that's now our relationship that we can use to connect this angle that the pole makes with this real axis and this hypotenuse omega sub n. So now we have zeta is equal to cosine theta. If we know where the pole is, we can find zeta, we can find theta, we can find sigma, omega sub d, the natural frequency. All of that is available to us. What we want to do in this lab is think about how can we change the system behavior or these pole locations without physically going up and changing the dash pot B, the spring constant K, or this hardware coefficient K sub HW, or the mass 1 over m. Is there any way that we can now adjust the dynamics, change the behavior of that by some other means than mechanically going in and changing the physical system parameters? And obviously I'm trying to set this up to have you thinking about, well, if we could in fact measure this velocity and feed that back in to make up some of the input, maybe with a gain K sub 2, feed this position and feed it back with a gain K1, we now might be in business in terms of changing the dynamic behavior of that system. And that's actually what we want to do. We can then use feedback. We'll measure the position or the velocity or a linear combination or some combination, or we could measure independently position and velocity. So there's both. We can scale the whatever signals we've measured, and in this particular lab number 2, we are going to just scale those with a constant, and we'll feed those scaled signals back into the input U. We're using constant gain feedback in this lab. Here's now the block diagram of that. I've tried to, in red, emphasize our physical system, and then we can go in. We're assuming now that we can go in and measure the position x. We can measure the velocity x prime, scale those with k1 and k2 respectively, and use those to help us create an input signal u. Now we can write our input signal u, which is the output of that leftmost summing junction, as this combination of all of the input signals going into that summing junction. The input structure then in this lab is minus k1x, so k1 is scaling the position, minus k2x prime, k2 is scaling the velocity, and k sub pf, that's our reference input scaling factor. If we now incorporate that input, or integrate that, or maybe integrate's a bad word since we've got integrators here, but let's now apply this input in where it belongs in our dynamic equation. Here's where I'm suggesting we want to introduce that input u that we've now created by measuring position and velocity, scaling those with k1 and k2, and in this particular lab we're actually going to start off by just measuring the velocity. So we're going to throw that signal away or not use it and see what we can change by just scaling velocity and feeding it back. Then in the last part of the lab we will adjust all three constants, k1, k2, and k sub pf. If we apply that input structure now to this differential equation and combine terms, we can now see that in fact we've modified the damping coefficient b to now be a b bar, where b bar contains the original damping b plus a scaled version of our velocity, where it's scaled coming through our hardware gain coefficient k sub hardware k sub 2. Likewise, our spring constant now we've changed to be k plus k hardware k1, and we have our reference input coming in through k sub pf. B bar, the modified damping coefficient, is a result of having velocity feedback. We've now changed the spring constant with position feedback, and we can now Laplace transform that new differential equation with feedback to produce a closed loop transfer function. Now we have a closed loop system, and we now have modified our denominator expression, and that's going to then mean that we have the ability to change the dynamic behavior of our system by introducing velocity feedback or position feedback or both, and that will now allow us to manipulate the denominator polynomial, which influences our system behavior. Let's now recall the standard denominator expressions, and we could either write it in rectangular form where we have minus sigma plus and minus j omega sub d, and that gives rise to this second order expression s squared plus 2 sigma s plus the quantity sigma squared plus omega sub d squared. Or you may have seen this in other courses or in this course, writing it in terms of our damping ratio zeta. Remember where zeta comes from. That is connected to the angle that those poles make in the complex S-plane, and our natural frequency omega sub n is the distance that pole is away from the origin. you should now be starting to see, oh, sigma and omega sub d, that's the real component and the imaginary component. Zeta is related to the angle, omega sub n is the hypotenuse. We now have all these different ways of thinking about where those poles are in the complex S-plane and how we might be able to adjust those by the appropriate feedback signals. Now I've replaced the X, I've moved it a little bit, and I've indicated it by a triangle. That's now our pole location, and I'm trying to emphasize that even if we have these standard variables, omega sub n, the natural frequency, the damped frequency, omega sub d, or the damping coefficient, sigma, I'm now saying those have been modified to yield hatted variables. So those are not what we started with in the original system. We now want to change those by position and velocity feedback. Let's look at some examples of how we might do that. Suppose somebody wasn't happy with the overshoot properties of our system. We wanted more damping. Suppose we wanted to double our damping. Here is our damping that we started with in our original system, B over M, with just the open loop behavior. If we now double that by a factor of 2, then we could do that with velocity feedback, since we now know how that coefficient or that term is changed by velocity feedback into B plus K hardware K2 over M. We can now solve for K sub 2, which if we scale both sides or multiply through by M on both sides, we now have 2B is equal to B plus K hardware K sub 2. We can subtract B from both sides, and now we have B is equal to K hardware K sub 2. And if we're simply trying to find what is this scaling factor that we want to weight our velocity signal by in order to double the damping that we started with, we divide both sides by K hardware, and we can now find that the gain on our velocity, if we're trying to double our damping, is going to be B over K hardware. Suppose we want to modify the system behavior a little bit more. By that I mean we want more than just changing the damping. Suppose we want to have the following performance properties of our new system. Suppose we want a new natural frequency, omega sub n hat, of 35 radians per second. Remember, that's now a distance from the origin to the pole of 35 in the complex S-plane. We want a new percent overshoot, and that now means, oh, we're changing the angle that that pole makes with the real axis. We want it to be 10%, which, if you remember your open loop behavior, you were maybe looking at percent overshoots in the 70s and not 10%, and your natural frequencies were probably in the 15 to 20 range, not 35. And suppose we want a DC gain of 1. So we're significantly changing. And what's that DC gain of 1? That means that we want the output to track the reference input exactly if we have a DC gain of 1 after all of the transients have died down or the transients have dissipated. We want 3 things to now be achieved. And remember, we actually had 3 independent gains to play with, and we were assuming that we had independent access to the position signal and the velocity signal. In lab number 3, we won't make that assumption. We will just say, oh, I only have access to the position. Well, I really want the velocity. Well, if you remember your calculus, you can figure out, oh, I could actually obtain the velocity from the position if I simply differentiated. So maybe I can do some signal processing. Maybe I can measure the position and do some processing on that position and say, oh, I can now get a derivative from that. Now maybe I can use position and velocity by simply measuring one signal. That's what we will start doing in lab number 3, but in this lab we're assuming we have access to the position, the velocity, and we are going to introduce this reference input r of t that we now use as units of counts. If we now connect these desired performance specifications to the system that we have with feedback, then you can see that that constant term in the denominator with feedback is k plus k hardware k1 over m, but in the standard notation that's the square of the natural frequency, and if we wanted a natural frequency of 35, we just equate those two terms. Solve for K1. K was our spring constant, M is our mass, K hardware we found from lab 1. We're now introducing a new natural frequency of 35. We square that, and we can now solve for this position feedback gain, K sub 1. If we're after a 10% overshoot, we can plug that into our overshoot formula or look at a particular percent overshoot zeta curve and find that, oh, for a 10% overshoot, we read across and read down, we need a zeta of about 0.6. Now we need the damping term, which is 2 zeta hat omega sub n hat. I'm hatting those to remind you that those are not the original system's zeta and omega sub n. These are the new ones that we're trying to achieve. We want these new system behaviors of damping ratio and natural frequency to be influenced by the velocity feedback term in this particular case. The 2 zeta hat omega sub n hat will then be b plus k hardware k2 over m. We solve that for k sub 2, and that now produces our velocity feedback gain. And remember, zeta hat needs to be 0.6 to give us a percent overshoot of 10%, and our natural frequency, we said, oh, let's make our natural frequency a little bit bigger just to show or illustrate that indeed we can modify the characteristics of the system, change the pole locations by full state feedback. In this case, that corresponds to having access to the position and access to the velocity. Last, in terms of our specification, is the DC gain specification. We want our closed loop transfer function at DC, or when S is equal to 0, that's DC, we want that to equal 1. If we set T sub C, that formula, evaluate that at S equal to 0, we have this ratio of the numerator over the constant in the denominator. The m's in the denominator of the numerator and the denominator of the denominator cancel, and we're left with k hardware kpf over k plus k hardware k1 equaling 1. K is our spring constant. K hardware is a property of our system. K1 we just calculated to give us our new natural frequency of 35 radians per second. K sub pf is the unknown that we're solving for in this equation. We cross multiply, divide by K hardware, and we end up then with our reference input gain being K1, which was used to adjust our natural frequency, the spring constant of our original system K divided by K hardware that we calculated from lab number 1. That should give you then the information that you need to create the answers on exercise sheet number 2 for lab number 2, and it all revolves around closed loop or pole locations and system behavior for a second order system. Good luck.